Hello everyone, my name's Christian. Rachel and I are going to be talking to you today about this little robot that we've been working on. But as an introduction, this is the Juno space probe. It's currently orbiting Jupiter. This magnometer here on the end, I had absolutely nothing to do with creating that, installing that or deploying that. But on the other side, this gravitational science unit here also had absolutely nothing to do with creating, deploying, or So this kind of science is a bit out of reach of most of us. But one day I got to the thinking that I'd like to build some kind of robot. So I've been basically a career software engineer, been writing corporate software for 20 years. And but I also tinker with electronics on the side, not expert level, but enough to be dangerous. So I thought, everyone's into drones at the moment. Drones are cool, but the problem with sort of exploration robotics is the drones don't really have much of a range. So I got to thinking, cross the land. Problem with land is there's roads and mountains and people and stuff in the way. I thought the ocean is a great unexplored expanse. Not much things to bump into, not many people there to run off with your robot when they see it wandering around. So Rachel and I live in Melbourne, so I set myself a target of building something that could swim from Melbourne to Antarctica. 3,044 kilometres. I realise that dream is probably, maybe not so practical, but I'm going to give it a go. We're going to go through a series of incremental steps and let's see how far we can get. So, electronics. We've probably all heard of the Raspberry Pi. This is a little Raspberry Pi here. Basically, well, I wouldn't even call it an embedded, technically it's an embedded microcontroller, but it's a AS 700 megahertz ARM processor that runs Linux, and from all intents and purposes is a fully fledged development environment. But it has some extra abilities that other small computers don't have, which is general purpose I/O, so we can connect different devices to it that we like, such as these things. Compass module, there's a GPS module. Probably all heard of Arduino as well. Arduino is the sort of the lower powered 8-bit microprocessor stuff, but all the components and gizmos that you can connect in a lot of ways interconnectable. So I chose the Raspberry Pi Model A because you can get, this is like a single core processor, and you can get the new quad core processor and stuff in the most recent Raspberry Pi, but this is low power, 90 milliamps is about the maximum power that it will use. So, but before I thought of building anything that I would actually put in the ocean that would then probably sort of capsize and never see again, I thought I'll go through a prototyping stage of, well, I'll actually build something that proves the concept of a watercraft, but I'll do it on land. So I made this thing here called Nix-1. So I had to think of a name, went through, Googled lists of Greek gods, and Nix looked fine and couldn't think of much else that was conflicting names or anybody else was using it. So I went ahead with Nix-1. So this is basically, if we turn its underbelly, basically just went to eBay, bought a whole bunch of parts, ordered them, stuck them together. So 10-watt solar panel, basically there. Little compass module. There's the Raspberry Pi. That's actually the older version of the Raspberry Pi there with the giant SD card on it. A trolley wheel from $2 shop. 4G internet dongle. And there's a little camera module. The GPS is on the top side, obviously, because this little surface here is aerial, so we're going to need reception. And probably most of this stuff's just connected with point-to-point wiring. Probably the most elaborate piece of circuitry here is the 7508 voltage regulator that I use to regulate 5 volts onto the into the Pi. And then I went and just bought some some basic, they're called gearhead motors. They're just a simple motor with a gearing mechanism built in that you can stick a wheel on. Highly advanced piece of bent aluminum ruler there as a structural support for the wheels. Marita Cheng, the founder of RoboGirls, looked at those pieces of bent steel and looked at me very disapprovingly. It's probably the weakest point of my design there, but it works. Solar charger, little battery, yeah, and there it is. So what's the fundamental principle of basically exploration? We're going to navigate, we just want to go from one place to another. We're going to navigate through a series of waypoints. I call them targets in my world. And simple principle, I timed, so when it's going forwards or backwards, both motors are either full forward or full reverse. And what I did is I timed how long it takes to turn 360 degrees, 4.8 seconds. So that gives me a ratio. So we get a compass heading, this is where we're going, this is the target. It will trolley along for 10 seconds at a time, recheck its bearings, and then turn to compensate to work out where it needs to go. So I took it to the park, and this is, so all the telemetry, all the data that it's been processing as it's been wandering around has been recorded. So I've been able to sort of play back this telemetry onto a Google map, and you can see that it kind of veers off and the grass is unstable, so it sort of goes off in different directions, and even on flat ground it doesn't drive perfectly straight, but it doesn't matter. It just keeps compensating, and there were 4 waypoints on each corner, and went a bit funny there, but that worked. It's got a camera built onto it, and what I can do is it can tweet right from the module. No reason to not have all that stuff on board. So that worked. So getting into the water. The Blue Robotics T100 thrusters. I sent them from the future to save, no I didn't. Startup company in California. They've been very supportive of my project and they're very supportive of everybody else's projects in the same sphere. A bunch of young guys who like marine exploration stuff, make a lot of subs, but marine thrusters aren't really a common item, and that's why they're very expensive. And they're also commonly just made of steel and expensive components. They took the approach of, this is pretty much all plastic. Apart from the motor coils, there's not much in there that isn't plastic. Because it's fully submerged, it doesn't need it's water lubricated, water cooled. So they've been very successful. The other piece of the puzzle, when we get further offshore on the 4G internet's not going to work anymore, is satellite module. This is called a rock block. There's a constellation of 66 satellites plus spares whizzing about our heads right now. They're going 27,000 kilometres an hour, and they're 781 kilometres above our heads. And they're creating a series of sort of basically like cellular phone coverage points, but they're constantly moving. And then when this thing needs to communicate, it's just basically trying to pick one that's passing at the time. Technically it's called a modem, but this particular device doesn't have a persistent connection. It's sort of the equivalent of an SMS. You send up to 340 bytes at a time, and you receive up to 270 bytes at a time. Not much, but it's relatively inexpensive as communication goes. You might pay $1 or something, or less than that if you buy in bulk for your messages. But if you're sending them, say, a couple of times a day, or just not that often, or when the robot decides it needs something that's important to say, it can communicate. So, steering on the... So, same principle for steering. We've got a target, we're heading. Basically, you just need to change direction to head there. Except these thrusters are... we've got two thrusters, and they're basically a scale of power from 0 to full thrust. So I've got this sort of baseline that I call impulse power, just to be a little bit Star Trek. So if I set the robot to 50% impulse power, both thrusters come at 50%. If I decide to need to steer over, I'll adjust a steering value, which will proportionally bring one thruster up and the other thruster down to steer it over. There's no rudders, nothing fancy. I went and bought a Boogieboard from the sports store, and I went to Bunnings and bought some plastic pipe, and I bought double-sided tape and some zip ties and a marine solar panel, and I just sort of worked out how I could sort of connect these together and create something that kind of floated around. And here it is. This is Nix 1A, I guess you'd call it. It's had a couple of iterations. But as you can see in this, this is its first journey. It's looking a bit CSIRO there with the tube on the back of it. But it's moving around. In a second here, I'll be able to pick up the back, and you'll see the thrusters in action. So I'm out there in the water, and Rachel was actually on the beach with this Mac here, steering it around, driving it around. I threw in this picture because it's an epic picture. It was actually taken by Con, the guy who runs the Melbourne Java users group. What you don't know, what this picture doesn't really tell you, is that immediately after that it flipped over, filled with water, and we went home for the day. But the latest version, well, what you find is once you drill a certain number of holes into a Boogieboard, it doesn't really become a Boogieboard anymore. It kind of loses its structural integrity. I was working out different ways to put the battery. So you can see here I've basically got a small battery sitting on the top. This needs just to work. That wasn't a sustainable design. This is the slightly more attractive version, where I've replaced that big tube, which I thought was a great idea at the time, but was just really impossible to get in and do any maintenance of, with a plastic special sealed container I bought from Bunnings that can be open and closed, and I've got cable glands here to get the cabling in and out. And this is Nix 2 out of the water. As you can see, it's just basically plumbing parts that can be easily worked and connected together, and it's actually quite strong. And this is from the bottom, and what you can see there is that the keel is a 22 amp hour lead acid battery that I've waterproofed at the top and sort of strapped to the bottom of the board. And what that does is, obviously that's quite heavy and keeps weight down the bottom, so that if it wants to flip, it's very likely to come back down. And the battery had to go somewhere. I looked at lithium battery designs and various optimizations. Lithium batteries are really difficult to charge. They're got all sorts of problems. Also because they kind of explode when they're in water. That was another problem I really didn't want to deal with. And again, $100 battery, and it works. Nice and simple design. Some of the gizmos here with the back open. Raspberry Pi is buried down there. Speed controllers, the coil controllers for the thrusters, and a multi-point tracking solar charge controller there. So how does this all work from a software perspective? So I've created this application called the Mothership, and it basically runs a lot of the same sort of codes. I call it the Nix runtime. This is the runtime that runs on the device, and then there's UDP telemetry that goes back and forwards between the control application. And this is playing back telemetry. You see a clock here. You'll see we're actually running it back faster than real time. I'm specifically playing this back faster than real time, just because it would, takes quite a while to play back otherwise. So every time you see a yellow circle, that's a tweet. Take a picture, tweet, and so carry it out into the water. Let it go. You'll see the thrusters come up here, 25% thrust, it's coming out. And then when the steering goes crazy, you'll know that it's on autopilot. I've set a series of targets, of waypoints, and that's it autonomously swimming through those points. Quite smooth, I'd say. Took a picture. When it gets to the last point, I have to hurry up and give it some more points to swim through. Otherwise, it'll stop. I have nothing to do. So it can do that for hours, and has done that for hours. I've wanted to take it a lot further offshore, but with electronics and salt water, and there's always been sort of problems and random crashes, and so for now we've stayed fairly close to shore, but you can see the scale there of the size of people and beach. That's still a reasonable distance. We're getting other telemetry here, voltage, ampage on the battery, bearing, of course. And this is one of its tweeted pictures here. And as I said, the code base that is running on the Mothership, also running on the device, means that when it tweets, it can go to Google Maps, get the picture, plot the point, overlay the telemetry data, and then send that straight to Twitter. A lot of seaweed in close to shore in Port Phillip Bay in Melbourne. We've got made a web version as well. So this again is playing back telemetry. You can see here I've graphed the thrust data on that graph, and you can see that basically symmetrical because the power level, say 38. So basically, say 37, 38% thrust, and we're getting the differential thrust. That big spike there was it had reached a waypoint, and it was steering hard over to get straight onto the next one. My Mac doesn't really like salt water much, so we have an Android client. Rachel's going to talk to us about that soon. But in the meantime, been working on some other algorithms that would be part of a working set of modes that the craft's going to be in. This red square on the corner here is actually, you'll notice in other videos that it's actually green. That tells me if we don't receive any telemetry data in 2 seconds, then the square goes red. We're going to run a simulation mode because there's no actual telemetry. It's going to stay red, but that's irrelevant. So basically we've got a code base that runs, and I've applied what we call sort of a functional approach to the code, because robotics and anything embedded is very, very stateful. You've got telemetry, you've got data coming in off different devices. You've got what mode am I in? In software, we try to apply sort of a functional stateless approach to everything. So what I've got is sort of a master event loop that it's currently triggered by the incoming GPS telemetry of 4 times a second. So 4 times a second, it will run the event loop, which I'll get to in a moment. And all the hardware devices, I've created simulations. So I've got a simulation thrusters and a simulation GPS. The simulation thrusters send a random nudge to the simulation GPS to say, we've probably gone in this direction a bit, with a bit of random to simulate real ocean conditions. And then I've also got like ocean currents and so forth. So that I can, and also the time, the simulation code will run with a simulated clock so that I can run a mission at much faster than real time and just basically see how everything tracks. So, hold position. So what happens if we just want to stay dead in the water? Turn off the motors, what do you think is going to happen? It's just going to float away. So it's going to power in here, stop. We've got two circles, inner circle and an outer circle. This is a simulated current drift. You can see the thrusters aren't doing anything. As soon as it hits that outer circle, it's going to power back to the inner circle and then power down again. Floats again, back again. The point of having two circles rather than one is that if it was just one circle, it would just sort of tick back over onto the inside and probably spend a lot of time burning power there unnecessarily. So the next demo is, that I have simulated here, is hold position, track to next target. So let's say we've stopped for the night because battery power is low and battery power is low, but we're still tracking towards a target that's we're going to get to the next day. What I'm going to allow it to do is basically uses that same hold position algorithm, but if it's actually floating towards the target, reset the hold position towards the target so that we don't have to swim back. So we've actually passed out there. We're still closer to this target, but in a second, it'll realise that we've actually gotten further away. Reset to there, powers in here towards that centre, and floats out. And I'll keep doing that. And these little sections in here are the only sections where it was under power. So this gives you the best battery usage. I put a slide in here and it was to remind me about something, and I can't remember. No, I can't remember what it was. Why UDP? For those who don't know what UDP is, well, just thinking back to the keynote this morning about the software stack. IP layer knows nothing about transport, knows nothing about stateful connections, is just throwing around packets. So UDP packets are just fire and forget. You don't know if they've been received, but the benefit of that is, so if I'm on this 4G connection and reception's getting patchy and it's trying to open a TCP connection and then maybe try to do an SSL negotiation on top of that, and reception drops out, odds are you're going to get stuck sockets, retries, bad news. So I'm going to use UDP for our transport. The other reason, the thing related to the UDP is that, as I mentioned about this satellite module that can send 340 bytes at a time, you also get charged in 50 byte intervals. So the smaller you can make the message, the better. And also because the smaller that message is, the more data you can put in it. So I've written a codec that will take a Java bean, Java value object, pull out the values, not even the names, because they're going to be symmetrically transcoded on the other side, and pack the values down in the smallest number of bits possible. So a Boolean that can't be null uses 1 bit. A Boolean that can be null uses 2 bits. 1 bit to say if it's null, and then, well, maybe 2 bits, 1.5 bits. Integers get packed into small values. strings have their lower and higher bounds reduced to the smallest number of bits to pack a message into a small space possible. So in part of doing that, I also just we use the same code for the BuDP. So the software stack: Raspberry and Linux, as I mentioned at the bottom, Java. When I started out the project, I thought, oh, this might be an opportunity to use some other language, some other cooler, hipper language. But I thought, no, I've been writing a lot of Java over the years, and for me, it's a rapid development environment because I can rapidly develop it, and I get all the enterprisey benefits of that. And then there's a library called Py4j. This is what Py4j does. That gives you access to the GPIO and the serial and the COM ports and all that kind of thing. So it's basically a bridging layer. So I created a library called B9, named after the robot from Lost in Space. And every time I needed to basically create a device driver for one of the devices I was using, put it on GitHub, open source it. So the Blue ESC T100/200 marine thrusters. Blue ESC was a controller that they'd created that used the I2C protocol to basically control your thrusters and get sort of that voltage data and the ampage and all this cool data comes back from. Then you've got pulse width modulated servo drivers. They're a more common way of driving servos, whether they're thrusters or motors of any kind. The satellite is basically AT haze commands. Sort of no Java support for that anywhere, so I had to write all that myself. GPS parsing. So a GPS is basically a device you connect to serial and gives you a list of strings, comma-separated values that have a type on the front and a bunch of ASCII data that you pull out, and that gives you all the data that the GPS wants to give you. The HMC 2883L compass module, triple axis magnetometer, which returns some crazy values and some math that I had to get off Stack Overflow to convert into a 360-degree compass bearing. A Wii Classic controller, just because I had one. Raspberry Pi module. A lot of the spatial math stuff. This is all heavy on distances and radiuses and diameter of the Earth calculations. Again, I didn't write any of this math. I just found it on Stack Overflow and wrapped it up neatly. UDP transceivers, the compact binary symmetric serialization. I have to think of a better name for that one. And the abstract time system. Not much to it in itself, but just a neat way of creating a system clock that isn't necessarily a real system clock that can be run at any speed. A lot of it's making its way to Google Cloud at the moment. This isn't fully implemented yet. This is our preferred state. We have a UDP load balancer using cloud storage right now for after it does the tweet, pushes up the raw photograph and then the overlaid photograph up to a bucket. Satellite provider will actually post to an endpoint. This is a good use case for a cloud function. I don't necessarily want to build it into a non-relevant other application because all that's going to do is hook that into Cloud Pub Sub. So we're going to decouple our Pub Sub stuff and App Engine for the front end that I showed you before, and then our redundant relay servers. Just a quick little slide there with the after it had taken that picture, it pushed it up to Google Cloud. Phases. Now this is my implementation of my method of solving or trying to solve the problem of statefulness of, as I said, you've got device data coming in at different times, and then you've got what the modality of the robot. Is it being manually controlled? Is it at a waypoint? Has it reached its waypoint? Anyway, you'll get an idea when I move on to the next slide of, so this is the current phases that I have implemented a pre-phase happens at the beginning. These always execute. Collect the device data from the devices, store that in a state that the rest of the phases will access. So those values aren't going to change in that time, snapshotted there. Got ping packets, respond to ping packets. First phase is return to base. This was something that was implemented at Rachael's insistence, that if it loses communication with the mothership for more than a specified amount of time, say 5 minutes, it will drop whatever it's doing, set a target back to the beach, home base, and power through there. Most of the time that's not going to execute, so it will move to the next one. If it's in a hold position phase, then it will apply those calculations for hold position. Assuming it's not hold position, autopilot, which is tracking the targets, and then finally, if it's not doing any of those other things, it makes it down to the manual control. And now I think it's Rachael's turn to tell us about her work with Android.
Thank you. Oh, can you take? Good morning. Okay, hi, my name is Rachael Colley. I am a software development trainer from Melbourne. Been teaching software development disciplines for probably about 12 years now. Lots of programming and coding stuff, and in more recent years, mobile apps, including Android. So so I'm here today to talk about my contribution to Nix's story, which is building a support app on Android just for test missions. I'd like to thank Christian for inviting me to tell that part of the story. So around the time that Christian was, at one stage I was planning a crazy walk from southern France to the eastern tip of Spain, which everyone was telling me was quite crazy. But around the same time, Christian was actually planning to send an autonomous marine craft many thousands of kilometres to Antarctica, and people said that was nuts. But I could relate. The hike nearly killed me, by the way, but I'm still here. I became involved with the project basically because I live with it. I live with Christian. I've actually witnessed all of this come together. And to be honest, I didn't really pay much attention to the project for the longest time. Christian spent a very long time getting together the initial prototype, so the actual build, putting together all the components, writing the initial lot of software. But a day came when he said, "Let's go to the park and let's try it out." And I was like, yeah, okay, and tag along. And even though I'd been, watching all this happen and kind of listening to it happen for a long time and very blasé towards it, I actually had this real wow moment when I watched Nix 1, the land-based guy, actually track its targets in our very large local park. So that was actually a real unexpected delight. So it's nice when you can still be delighted by these things, and it was a real wow moment. So much more time passes by and we're moving from the land-based prototype to our water prototype, which is Christian's water prototype, of course. And I witnessed firsthand the challenges of mixing technology with seawater and wind and sand. And I was often the helper who was holding on to MacBooks or wiping things down while Christian ran down the beach or had to run out into the water. So it became very desirable to be able to have a smaller version of the Mothership application that you've seen previously on a smaller, less expensive handheld device, which is a bit more waterproofable. Because no one really wants to be standing in the, waist deep in water with a MacBook in one hand and a runaway robot in the other, and that sort of stuff was happening. So it became very desirable to have that kind of ability. So our wish list. Okay, so once again, the app is just for the test mission environment. So Port Phillip Bay, and the ability to do a few of the things that the Mothership can do. Not everything, but a few of the things that are great to have during a test mission when you don't want to be standing waist deep in water with your MacBook. So, for instance, things like being able to start and stop the craft, being able to set new targets out on the bay for Nix to swim to. And, of course, visualising the telemetry and Nix's current position on a map, and return to base, being able to sort of press a panic button and say, come back, come back. So we've checked off some of those items, but as I'm sure you can imagine, testing these things is fairly slow, cold work during winter, and at least for me, a lot of stuff kind of grinds to a halt because I don't own a wetsuit. So, look, this diagram looks pretty much the same, whichever client's on the other end of the relay. So basically we have all of our communication, UDP over 4G, especially out in the bay environment, with the relay server sitting in between. Throw into that our Google Maps player as well to overlay all of our data on. So, why Android? Why? Okay, so I have a bit of a love-hate relationship with Android. I've been working with it for a while, which is one of the reasons I jumped into the project. So we chose Android because the Nix runtime is actually written in Java, which is native Android speak. Are there any Android developers here or people who've had a play with it? So do you kind of have a love-hate thing with it as well, or is it just me? It's hard, right? It's a dependency hell. Another really good reason, was I'd had experience with a few complex Android projects where I'd worked with networking and animation, some of the kinds of things we were going to need, and done a few cool things with other device features like NFC and stuff like that. So I figured, I could have a crack at this. And I was pretty keen to get my hands dirty again. And also working in education, education is a great opportunity to innovate, but if the innovative, challenging projects aren't actually coming to you, you really do need to make them up to keep your teeth sharp. And I've been very conscious of always making sure I've got something that's really killing me to work on outside of education to actually challenge myself and keep my teeth sharp. So, and I'm also generally just a glutton for punishment. So yeah, that's why we chose Android. Building a multi-threaded mobile application is a lot of fun. It's been quite a hair-raising experience. I've tried to model some of the main processes in the app as it's running. The telemetry data starts as Java value types on board Nix, and it gets passed through the relay server. I've got the Nix runtime on my side, which is very good at actually passing me all the things that my app needs. However, I have had to develop a core that sits between the runtime and the Android platform to make sure that everything can play well together. So, for instance, things like being able to collect all of Nix's location coordinates in order so that that information can actually be drawn on an Android canvas. So that, it doesn't naturally come to me in great shape to perform that action. So a fair bit of processing to get it in the right shape for that. calculations, some of the data types that come through from Nix need to sort of be worked a little bit so that they can be passed through for performing calculations. And look, an Android activity is akin to a sort of a web page for people who aren't familiar with Android. So a web form. So an Android activity goes through many events, has many events in its life cycle, and quite often knowing sort of where to code, where to execute your code is a greater consideration than actually the code itself, particularly when you've got so many processes going on. So that's absolutely hands down been the biggest challenge for me in building this app, with so much data coming in and also data going out as well when we're sending override commands. So it's been a really, really big challenge. All right, so here's just a static image of the UI. Looks very much like the Mothership. So we can see there we've got Nix on its current path. The circles are the targets. We've got a couple of tweets there. And I think this one, if I press, I think I've got a little animation there. So this is it. I think I've sped this one up 8 times. It shouldn't go for too long there. So we can see all of the same stuff as we can see in the Mothership. So if we press those dials on the UI, we get with some of them we get the opportunity to override commands. So for instance, with speed and steer, doesn't look great. I know it's very basic, but it does work when you touch it. We get the opportunity to actually override things like speed and steer, which is very desirable when you're standing all windswept and interesting and up to your waist in seawater. As we continue to check off the wish list, we'll be able to add a touch, hit return to base and stuff like that as well. So one of this is actually a post-mortem of or an analysis of one of the test missions, one of Nix's earliest test missions, which is, I guess, was another reason why we thought it'd be a good opportunity to build a smaller handheld device so that we could actually maybe swim after the craft and control it a little bit. So this day Nix lost its mind, as you can see here. So if you follow the trajectory, you can see it's autopiloting along. It loses its mind here. Can you see it lose its mind? You can actually see it. And it's kind of under its own steam, but it's kind of not behaving the way it's meant to. We've managed to get it under manual control here, but it's still sort of leaving us. It's getting further and further down the beach, and I get so stressed out when this thing just sails off, because I just see all this time and money just going. Christian's so calm. So it's getting to about here, and I'm really panicking, and I'm up here just going, oh my God, and I'm watching Christian and I'm thinking he's not going to swim out there. Please don't swim out there. He's not a strong enough swimmer. And, you know, some footballers can swim, right? A bunch of them just seem to be there at that time, and we just can't. I kind of ran out, excuse me, did that trick. And they were very happy to swim out and, well, some guys, the footy guys, and actually bring it in for us, bring it in to shore. So, yeah, that was the day Nix lost its mind. So what's next? Look, over the next summer mission period, when the weather's warmer and the water is warmer, I expect to finish off our wish list for our test mission app, which will give me more time to roller skate along St Kilda foreshore, because that's actually what I really like doing down there, and less time actually managing MacBooks and helping Christian out. And of course, planning my next crazy thing, which is a hike through Central Australia. So thank you for your time.
Yeah, she says I'm brave about this thing. Like, I get unusually nervous doing the smallest production deployments at work. Text change, I get stress that the servers are going to get down. So what do? I build something like this that could just disappear and die on a whim. So can we guess where Nix is right now? Approaching the coast of Antarctica. No, he's not approaching the coast of Antarctica. But I really wanted to have a live demo. I really wanted to get Nix out in the bay in Melbourne and to be able to cut over live, but it didn't pan out. I didn't get volunteers. I actually had to rebuild the thruster mechanism recently, so I haven't tested it properly. So there's a whole bunch of reasons why that's not going to happen. But Nix is in Melbourne somewhere, alive and kicking. And let's find out where. Oh, green, telemetry data. In the middle of Caulfield Park, apparently. We're getting time code. We're getting a heading, sitting at 14 degrees. If I actually power up the thrusters there, they're actually spinning all the way, but you can't hear them, it's a bit far away, but they're actually all the way back in Melbourne, they're spinning. What we can do is we can find out what Nix is actually looking at right now by press the P command, which will give us a photograph, hopefully, in a second. There it is, dot appeared saying that it took the photograph, did the tweet, upload to Google Cloud, all that kind of thing. So let's quit out of the Mothership, drop back to Nix's Twitter page, Twitter profile, and see what he's up to. What's he doing? He's sitting with Mix One, drinking beer. Anyway, so back to the slide deck. Wrong way. Lessons learned. Prototype. As I said, Nix 1 was prototype of Nix 2. I knew the set of challenges I wished to solve in a more controlled, drier environment. Simplicity, say this from the point of view of a software engineer. I have had many criticisms of the design of the Nix is not hydrodynamic. It is a boogieboard with some bits of sticks sticking out the bottom with thrusters on there. It should be shaped like a yacht or something, but I'm not in a position to build that. And I've racked my brain on numerous designs. I've thought of catamaran designs. I've thought of many designs, but from I actually built it and it works point of view, this is currently the best design I have. Reproducibility. Remember when I said that Nix had flipped over and took on water and dead and went home? Took it home, found seawater had splashed onto this guy, pulled another one out of the drawer, popped it in, we're going again. A lot of these parts are reasonably cheap. You jump on eBay, you buy some parts, buy at least two. Triple axis magnometers cost about $1 or $2. So you buy 10 of those when you place an order. And I've gone through nearly 10 of them already. User existing skill sets. As I said, I've had people say, well, that should really have a rudder, not, just changing the power of the thrusters. No, I don't know how to build a rudder. I'm not building, and I don't need to build a rudder because my system of basically differential power on the thrusters seems to work really well. Waterproofing stuff is more difficult than I thought it would be, and probably the most important lesson is it's not perfect, but it works. Will the current design make it to Antarctica? No. The board's too brittle. The ratio of power coming into the board to charge, time per day, no good. It's pretty crashing waves. It's okay in the bay, but it wouldn't take an Antarctic ocean condition, probably snap it in But that doesn't mean that I'm not going to get to a better design that will be more stable. It's time for questions. Yeah.
So when I've done a very low-tech version of your Nix 1, with the turning, what I found was the rotation changed quite dramatically depending on the surface it was on.
Yeah.
Wondering if you had any advice to cater for those sort of conditions.
No, I found that on the grass it would slip, it wouldn't even steer straight. My method was that even if it was 10, 20, it doesn't matter how far out it was going to always correct. I guess you could do something like, so I wasn't using, Nix 1 didn't even use a proper compass module. It's originally, I didn't have the compass module working, and the GPS will actually give you a heading. It will say, based on your current, your previous locations, it will draw a line through there and say you're heading that way. Now that's fine if you're driving in a car or you've been walking down the street. The locations are that location data is pretty accurate. But when it's moving at 0.1 of a kilometre an hour and the GPS is not so accurate and it's darting about to start with, the heading was quite irregular. Anyway, my point was, if you are using the more accurate compass module, and you could turn at a speed where you could actually measure the amount of turn from the compass rather than, as well as just time-based, maybe that would improve its accuracy. I didn't go for fancy motor control with purposely on Nix 1. I just wanted it to do something. You can use, I could have used the same approach as Nix 2, which is proportional motor, pulse width modulated motors that would have accurate speed. But I just got a relay board that has 4 relays on it, and just on-off DC motors, and you can wire the relays in a way that you can reverse the polarity of the motors, so they can go forward or back. And I did that with like $5 worth of parts and simple software. Yeah. I didn't write, when I say the Pi camera driver for the B9 library, it's kind of cheating in that it calls the native camera software is really good and works, and it's just a wrapper to the native. I actually don't know what language, I guess it's probably written in Python, but whatever language is written in it, just calls the native a Pi camera command. Same with video. This will actually, I had it working at one stage and it wasn't really high priority, but I was streaming video from the camera as well and recording video. Yeah, as I said, everybody asked me about obstacle avoidance. The point of the ocean was there's not much out there, and even if it bumped into the side of a boat, it's probably going to recover. Obstacle avoidance, not, at least from a point of view of, you can probably route around known, or tell it something's there and route around it. But obstacle avoidance in the general sense wasn't a priority for anything.
Which was the most enjoyable, solving the problems of the actual craft or solving the software?
I guess both. I mean, I've sort of software engineer that just enjoying writing the software. But when, as Rachel said, when it just all came together, firstly for Nix 1, when we knew we set a waypoint down there. It just worked. And whilst there was a lot of struggles to get the Nix 2 design with the 2 thrusters and the angle, where I put them in the water and that kind of thing was just kind of a best guess, and it worked really smoothly. And at one point I actually got a bit arrogant in that I was doing a rebuild, and I'd put the battery on the bottom as the keel, and I thought, don't need those thrusters out there. I'm just going to put them in close together and glue them onto the side, araldite them onto the side of the battery, so I don't have all this stuff to worry about. Just wouldn't steer straight. Refused. They were just too close together. I guess the fact that that big square battery is in no way hydrodynamic and creates turbulence and problems, it just refused. And I thought, I might need to like overcompensate with the ratios of how much thrust on each side. Just wouldn't do it. I just had to peel those thrusters off and put them back on the sticks. Yeah, but yeah, to answer your question, just when it does what I hoped it to do. And we showed you the plotting the paths. We sat there for hours just plotting waypoints. We would swim through it. It's got boring. It's kind of like, yep, it's working.
But you knew how to solve those problems probably at the beginning in terms of, the fact of the code.
Yeah. I mean,
Whereas the other problems you'd never seen before and had to learn.
yeah. Well, most of the problems are in the slowest part was the physical engineering part. I have an interest in engineering, but I don't claim to be an engineer. If I wasn't a software engineer, I'd like to think I would be an industrial designer or something. It's cool to design things, but it's not where I'm at, so I just do what I can with what I got.
How would the Pi Zero go as alternative to the...
The Pi Zero would... I had a friend of mine saying, are you going to swap it out for Pi Zero? On principle. Yes, in theory, Pi Zero's still got USB. It would work. So even this tiny computer, the guts of it is just that little square in the middle, and the Pi Zero is a even smaller version of that. But then it's also about reproducibility. Pi Zero is a purposefully limited supply, not supposed to, you can't go buy them in bulk. They're supposed to be things that for equal access. Yeah.
So you mentioned that the power ratio was not sufficient to do the whole training. What was that power ratio, and what are you doing?
The power ratio is simply that it's a balance, and I'm also thinking about scale. I could actually build something that is even smaller than that. But then you've got a smaller surface area of the solar panel. But then you've got a smaller craft to move. You can build things bigger. Something bigger is going to be theoretically sturdier in the water, bigger surface area for capturing energy, but then it's a bigger thing to move. So it's finding this sweet spot. I realised that, especially with big waves and ocean conditions, that it is probably a bit small for what it's trying to achieve, but in calm water and that sort of thing, it's doing okay so far. So 40 watt battery, 40 watt solar panel, theoretical maximum, 22 amp hour battery, thrusters that will at full power use about 15 amps each, not that I actually push them to 100%. So you've got to balance these ratios of how much power is on the panel, which would then charge the battery. Battery isn't 100% efficient, so whilst it's charging, it's not taking full energy from there. But if it's under power while there's power on the solar panel, then you'll get 100% of that power will go to the thrusters. So there's the balancing act of how much power you can get, how much range you get per day, whether you can, if you were swimming at night, whether you need to actually stop or you can use the battery reserves and for how long. But having said that, I used the small battery for hours at a time, and my calculations were that it shouldn't have lasted as long as it did. So there's probably some more measurements and math involved to, and this reading real. This thing with telemetry, you read rather than just theoretical. Just go do it and read the real values and see how well it does. Yep. It's been about 3 years now, but I wouldn't say I've been working on it full time. It's just been there'll be weeks that I'll get a lot done, and then months will go by, especially in a cold winter. I really wish I had a pool. I don't even have a bathtub, so testing it is hard, and in Melbourne especially, because some days the bay is perfect, pure glassy water, and you're just like, oh, it'd just be great to be down there playing with my boat. And then other days you just want to get out there, but it's windy and terrible, and I think we actually did it on a few of those days and went, no, let's not come down here again and swim through seaweed and make the same mistakes. Yeah. Sorry? About UDP? Yeah.
It's taking the picture and sending it.
Yeah.
So is it our UDP or UDP protocol?
No, the UDP is just for the telemetry. Tweeting, Google Cloud Storage, that's just regular client libraries, TCP. Obviously that stuff's not going to work when you're out of 4G range and you've got 340 bytes at a time to deal with. But the idea could be that if it's, say, tracking the coastline and it's out of 4G range, it's going to fall back to satellite. As soon as it gets in range, sync up everything it can, proclaim its existence and so forth. So, any questions for Rachel? No? Yeah. All right. Thanks, everybody.